Good morning, everyone, and thanks for coming to this event. So, my name is Elias. So, I will be talking to you about the Cox regression, the non-proportional hazard assumption, and time-varying covariates. It's the first talk. So, here is a little bit of disclaimer, and then let's go to objectives. So, today, it's the first talk, so the main objective is to talk about the hazard ratios, Cox proportional hazard model, describe the methods, the assumption of this model, and describe what happens if how to deal with non-proportional hazards in Cox model. So here's the main objectives. So let's start with the hazard, introducing hazard. So probably most of you are familiar with it. So what is hazard? Hazard is a force of mortality or force of intensity. That's another interpretation of this. So it's an instantaneous failure rate at time t. So by another meaning, it's sort of a probability that individual will experience some event at time t, given that this individual has not experienced it before time t. So you can see the two graphs here. So I think the first graph comes from the study for time to chronic heart disease. And the second one is time to analyzes time to operation. So we have two graphs. In the top graph, you can see that the hazard function is sort of constant over time. So it stays constant, whereas in the second graph, you can see that the hazard function is high at time 0, then it goes down until time 2 and increases back again. So I hope this is all clear. So we will talk about the Cox proportional hazard regression. So this type of model is used in survival analysis in medicine. It's very common to use in order to analyze the study for time to event. So event can be death, any particular disease, or anything. So the most of the studies that we do is looking at the time to death from the baseline. So you see that there is a formula. So this is the formula for hazard function. So you can see that we have a hazard function for subject I at time t. So this hazard function is a function of time, coefficients, and covariates. So time is t, beta is the coefficients, which are unknown and have to be estimated. Z is the covariates. This is equal to multiplication of the baseline function, baseline hazard function, mu0t, and a risk score defined by Ri. The risk score itself is a function of coefficients beta and covariate z. The covariate z have a log linear contribution to the hazard function. You can see the rearrangement of the formula, and then the risk score is expressed in terms of the exponential of beta times z. So I hope this is all clear. I mean, this is just the basics. So this is how we define the hazard function. And very importantly, the first assumption is that our estimates beta, they do not depend on time. This is one of the assumptions we make. We will talk about another model later on, with time-dependent coefficients. but more on this later on. So, whenever we are fitting the Cox regression, that's Cox regression model, we are not estimating the hazard function itself. We are estimating the hazard ratio. So the hazard ratio is the ratio of two hazard functions. In this case, it's supposed to be two subjects, I and J, who differ in some covariate Z. So Z0 and Z1 corresponds to the difference covariates, suppose 0 and 1, respectively, but they are the same on in all other covariates, so all other risk factors. So whenever you take the ratio of these two hazard functions, the important part is that this hazard ratio is assumed to stay constant during the follow-up with respect to time. And because of this, the Cox model does not really make any assumption about the baseline function. We don't really need to make assumption, it does need to be estimated. So it's quite important that this is just an adjusted hazard ratio. So we have taken into account all the risk factors in the model. So far, so good. So as I said, like in these graphs, the important thing is to look at the hazard ratio. So we have two hazard functions in each plot, and the ratio of these two hazard functions stays constant. So whereas like in the second plot, you might see that the hazard functions itself, they go down until time year 2 and then go up, but the height between the two hazard functions stays the same. I think I have talked about it already. So I hope this is all clear. So yes, so we have some graphical methods. So we make a lot of assumptions about our models. But we need to check these assumptions either using a graphical methods or formal tests. So let's have a look at an example. So this is a data set that analyzes the patients with Parkinson's disease. So in total, we have 520 patients in this data set who were followed up for 17 years. So the main outcome is the time to death. So in total, in this data set, we have 266 events, which is event is a death. So the exposure, so we want to compare two different treatments, the new treatment versus a standard treatment. And we have some covariates, which is sex, so males and females, and age group. So you can see it on the slide. So we have fitted three models, three Cox regression models. So you can see the outputs in here. On the very top, you can see the result from the model which only has one covariate, which is a treatment. So it has a hazard ratio 1.21. So it basically shows that the new treatment is worse than standard treatment. But it is not significant because it doesn't cross 1. In the middle output, you see the output from another example is when we adjust the model for sex. So when we have adjusted model for sex, we have two hazard ratios, one for treatment and one for sex. So it shows that the sex does not really matter because hazard ratio is like almost 1. So, and both of them are not significant. However, very interestingly, in the third output, when we have adjusted for age group, our hazard ratios has changed. So what happened? So H is a very important covariate here. I think because in this study, when women entered the study, I think they were much older than men. So in this, so you can see that the hazard ratio of treatment has gone down to 1.16, and the hazard ratio of sex shows some benefit to females. So males is a baseline. And also, importantly, I haven't talked about it, we have some measure which is a concordance. So this measures the predictive ability of the model, sort of discriminability of the model, how good is the fit of our model. In the first two outputs, you see that it's about 0.5. But whenever we have introduced H covariate, it has improved. So the fit of our model has become better. Any questions?
What is the formula for concordance?
Sorry?
What is the formula for concordance?
I mean, it is some complicated formula. I think it looks at the events and times as a function of all the events and time to events. Yes.
Can you use the microphone?
I can explain. Concordance is basically concordance looks at the pairs of observations, and it compares the order of pairs ordered by the risk score compared to ordering on the time of death. So it's like a Kendall's correlation coefficient between the risk score and the time of death. And of course, when concordance is about 0.5, it means the model has no predictive power at all. You can toss a coin. Okay. But of course, when concordance is 0.7, the predictive ability of the model much better. And in survival analysis, concordance of about 0.7 to 0.8 is kind of a standard concordance for a good model. Well, but yeah, you'd be lucky.
It's not to one range.
Sorry, what?
It's not to one range.
Yes, it's correlation, yes.
So I will continue using this Parkinson data example. So we have fitted the model, but we of course want to check the assumptions of this model. So in this, we use the graph, in this slide, we use some graphical methods which plots the estimated survival functions using a Kaplan-Meier method against, I think against time. So you can either, I think we did not adjust for the covariates. So, but the most important thing about this graph is in the first graph on top, when we are comparing the survival functions. So survival function is a y-axis, that they should not cross. So whenever the two lines cross, the assumption of proportional hazards violates. So this is one of the graphical methods, so it will be very difficult to judge. On the second graph, you see that when we have adjusted model for treatment and age, the lines are sort of parallel, so they do not cross for sex. So we will look at some, so this is one way of looking at testing the non-proportional hazard assumption. Another way of testing it is looking at the survival functions, log survival functions against time. So here on top first, from the hazard model, we can obtain a survival function. Survival function is a probability of individual being alive. So S is a survival function, T is a time, Z is the covariates, as before. It is a function, it is equal to the exponential times the cumulative hazard. So capital mu 0 is a cumulative hazard, which is like the sum of baseline functions. Yes. So whenever we take the double log of this function, we can have a look at how it varies against time for covariates. We will look at it in a plot. So two lines should be parallel if we want the proportional hazard assumptions to be met. So this plot shows that the lines are not parallel at all. They sort of cross in the end. We can try to fit this model for adjusted or unadjusted. We can try to make this plot for adjusted and unadjusted model, but I think it was an adjusted model. So we have, this plot shows that the proportional hazard assumption is violated again. So let's go next. So this was the graphical methods, but we can also use the formal tests, which are based on residuals. So what is the residual? The residual is the difference between observed value and the predicted value. Some basic statistics. However, in survival analysis, because we censor the data, it is not straightforward. So there are many types of residuals in survival analysis and in statistics in general, but we will only concentrate on Cox-Snell and Schoenfeld residuals in here. So we want to look at the Cox-Snell residual in order to assess the goodness of fit. The Cox-Snell residuals are the minus log of estimated survival function, which is the cumulative hazard at time of death or time of censoring. If the model is correct and we have proportional hazard assumptions to behold, then the Cox-Snell residual should have sort of an exponential distribution. We can have a look at using a QQ plot for Cox-Snell residuals. So using this plot, you see that in the beginning it is sort of a straight line, but then something happens at some particular after time 1.5 years. So still it's not 100% clear, but this plot shows the assumption is met. Let's have a look at some other tests. So Schoenfeld residuals.
Can I just stop there?
Yes.
What about that plot is telling you is met? Is it that its reasonably close to the y equals x?
Sorry?
It's because it's reasonably close that you can.
I mean, it is reasonably close,
Yeah.
but I feel like we need to do another test.
It's going to be close, surely, the data volume distributed.
Sorry?
Presumably it's only
Because if you have big values, it's not
distributed
yeah.
fairly uniformly. So you'd expect the top right hand portion of data to be almost minuscule.
Yes.
What I typically do with QQ plots is I will do a number of just simulations with the hypothesized distribution
With the
of
true
the
and-
sample size.
Mm-hmm.
And that just gives you an idea about how much variability would you expect to see at, particularly at the top end, where you're getting into the tails of the distribution, so you always expect deviations. So, if I saw something like that, I would certainly think that.
I think our sample size is quite small as well in this study, so compared to our big studies. So that's one way of doing it. Thanks, Andrew. So this is the QQ plot. So, but we also want to have a look at the Schoenfeld residuals. So the Schoenfeld residuals is the difference between the covariate, certain covariate Zi of subject I, who have experienced an event at time t, minus the weighted average of all covariates. So we want to look at the Schoenfeld residuals in order to perform a test which has the name Gram-Center-Neo test. I'm sorry for my spelling. I hope we spelled it right. So we want to look at the Schoenfeld residuals for each covariates and see and look at the correlation against time. So in the next slide, we have our covariates, treatment, sex, and age groups. So we want to look at the correlation between their Schoenfeld residuals and survival time. From this output, what you can see? You see that for sex, the Schoenfeld correlation is significant, whereas for treatment and age groups, they are not. So significant correlation indicates non-proportional hazards. And we can also have a look at our estimates for sex using a graphical method, so which you can see on the graph below. As you can see that the beta is sort of is not really constant across time. Particularly, I think it changes at time 9, year 9. So what do we do? So we have an assumption of non-proportional hazard is not met. We have to, one very obvious way is to include the time as a covariate, but we cannot include just time. It's better to include the log transformation of time as a covariate and look at if it gives us significant interactions between our covariates and time. So in this formula, you can see that we have our beta t is now the time varying coefficient, and before it was constant. So so you can see the rearrangement of beta t in terms of beta j times theta and gt. So gt is a log transformation of time. And we want to test the hypothesis if the theta is 0 or not. So if the theta is 0, then our coefficients do not vary with time. So if we fit the model with a log time, it is our interactions with of log time with covariates are quite significant. So you see it from the last 4 lines. So it's very sensitive, have to be careful. So we have concluded that the assumption of proportional hazards are not met. So what do? We can either stratify our analysis for Z covariate, but for some covariate, but not all of them, but only for the covariate that varies with time. So we can fit a model which does it for us. So in stratified model, we assume that our baseline hazards are different for this covariate, for group. So the only covariate which has hazard ratio that changes with time is our interest. So another way of doing it is just fit the separate models. So we will have a look at it using our example. So we want to fit separate models for the covariate. So in our case, it's sex. So another way of dealing with non-proportional hazard is to include the time-dependent effect. So we can split the time where the hazard ratio changes and look at different hazard ratios. Probably it's better to show you an example. So here is the stratified analysis for our data set. So our stratified analysis, we have stratified it by sex. So you can see the output in green box. And you can also compare it to the output above. I'm sorry, I need to mention that output above also in comparison to models before, we have included the interactions. It's very important to look at the interactions before you fit any model and try to make any conclusions. But in our case, the interactions are not significant. Interaction of sex with other covariates. So we can either stratify a Cox model, and we have stratified on sex and have output there in a green box, or we can fit a separate model, so separately for females, separately for males. It sounds very easy, but we have a cost that the estimate for sex is not there, so we don't really have an estimate for sex.
Can you explain why the green box doesn't have sex in it?
We have stratified on sex. So, I mean, this is the using, so you say that the baseline hazard varies for sex at some point of time. Is it okay?
Yeah.
So this is the graph before, but so we want to split the time into two parts. So one time is from time 0 to 9 years old, and another time is from 9 years old onwards. And we want to split the time for sex and have a look at how our hazard ratios change. So when we split the time, at the moment you see the two outputs for sex. These two outputs corresponds to two different time points. I have two different time intervals, from time 0 to 9 years old, to 9 years, to from 9 years onwards. And we can also have a look at our residuals. Now they are significant. They are not significant, sorry. So all is good. Before the residual for sex were significant. This is more consuming to do all this. You can split it into different intervals. But so it depends also on the software you're using. So if you have any questions, just let me know.
Okay, so we have some time now for questions, and it may well be that you might want to also go back to some particular slides that it's now open to the audience to put some questions or maybe make some comments on the first presentation. Yep. Yes, please do wait for a microphone.
Hi, thanks for a really interesting presentation. You sort of touched on at the end, it depends what software you're using, so I wonder if you have any advice on what software would be recommended for this sort of analysis.
We are using mostly R, so it is free software and has all the packages that you need. And I think it's once you start and try to use it, it's very easy. But there are, of course, other packages.
I think the main package which Ilyas was using in this presentation was survival package in R, which has the main tools for survival analysis, but you will see in later presentations, and we also use some more recent other packages to do the survival analysis, which incorporate more complicated methods.
Fantastic, thanks.
Any other questions or observations? Yep.
This is not a technical question, more about the practical. I assume that the presentation started off saying you're using methods which are common in medicine research. So is this a piece of original research which we've seen the results of? If so, where is it published, and is it of use in the medical world? I.e., is this a set of results which is going to be significant for doctors using different treatments?
Are you talking about this particular data set for Parkinson's disease? I think it's just a data set in survival package, if I'm not mistaken. It's just
So
like...
it's here just for illustration rather than...
Yes, just for illustration, not really our results.
Again, thanks very much. I guess I was interpreting your question more widely, actually. I was thinking the question was to what extent has this problem been previously addressed, or is this the first time it's been addressed? Because I'd have thought that in a huge amount of medical research, the duration since diagnosis is a fundamental factor. Clearly that's going to be time dependent if you look at time in the context of duration as opposed to calendar year or age.
Personally, don't know much about Parkinson's disease. Maybe Lina
Well,
can
no,
help.
this has nothing to do with Parkinson's disease. This is a general question. It's not at all related to the particular data set.
I think maybe I will try to answer your question. Yes, you are right that time since diagnosis is usually, hazards of time since diagnosis are usually time dependent. And you may well have this bathtub hazard we showed you to start with when, say, after operation, your hazard of dying is much higher, then it goes down, and then it goes up again, say. In this particular slide, we saw a very simple method of trying to cope with time-varying hazards. And this method is just try to split the time into 2 time intervals, first and second, or maybe 3 or 4. And so the hazard will be constant within each period. In this particular case, this seems to work, so that you can see that for sex, females are much better off in the first 9 years, is it? But in the subsequent period, they do not seem to be faring any better than men. But we will show in this workshop much more sophisticated methods of coping with time-dependent hazards. So this is just the simplest possible way to cope with them. Another thing I perhaps wanted to mention is that, at least between us, we kept talking about this workshop as a technical workshop. So basically the main function of this workshop is to try and talk about the methods more than about the results, even though we will tell you about the results. But the main emphasis here is about the methods, and results very often will come as an illustration of the method.
No, that's clear. Thanks very much. The results on a sort of semi-fictional data set are not themselves of interest is very much the method. But I guess the question is then if you come to publish this summer, it'd be interesting incorporating in that some form of sort of summary of other techniques for approaching the time dependency problem.
Keeping in mind that the sort of your point about we're here to sort of learning the technical or the methods. I mean, if you could maybe go and get the clicker and go back to plot of the Schoenfeld residuals, because it's just about so how is this constructed, this particular plot, and then also why in the plot do we see these bands of dots? So how do I interpret that in terms of whether the model is a good or a bad fit to the data?
So, I mean, the most important things, and I think you need to have a look at the line in the middle. This is the line for beta t for sex, so coefficient. So and beta t is a hazard ratio. So if the hazard ratio is constant,
yes,
it sort of stay constant.
Yes. Yeah.
But at the moment, you cannot really see a straight line, or like it varies with time.
Oh, yeah.
So, and you can also see the confidence intervals for it. So
and then what's the relevance of the dots in this plot then? So where do they fit in terms as a graphical diagnostic?
Cannot remember from head, but
I think this line here is just a smoothed feet over time, using some smoother basically, and the shape of the line corresponds to whatever line of the best fit across those points.
So points are observations.
All right. So, well, I suppose then, I mean, if I'm using that, then I'm trying to work out in my mind, well, does the revised model, is it a good fit or not? And so because I've not used this particular type of graphic before, so I don't know when I'm looking at this whether it's giving me confidence that I have a good model or not, because there's lots of dots that are outside of the confidence interval.
No, you shouldn't worry about the dots.
Right.
What
Yeah.
we are worrying about in this plot is exactly the shape of coefficients over time, because this is a plot to give you an idea about whether your hazards are changing over time.
Okay, right. And then is the smooth line in
This
the
is a
confidence
smooth
interval,
line.
is that derived from the dots?
Yes, it is
Yeah.
derived.
Okay,
Yeah, it
right.
is a line of the best fit, kind of describing relationship with those dots in time. Yes. But of course, our split into two time intervals here before 9 and after 9 is pretty arbitrary. But it does make sense, at least to the second interval, where you can see that the line, central line, is kind of flat from 9
Right.
on.
Yes. Yeah. Okay. Yeah.
That's a related question, please. Does the shape of that curve give you any clues to a functional form of the time dependence, or where you might split it?
It certainly gives you some idea of where you can split it, but it also gives you some idea of the dependence of hazard over time. And what we are going to do in later talks will be trying to put a kind of polynomial functional relationship of the coefficients over time.
So can you use the microphone actually, sorry?
Is there any practical reason to avoid empirically fitting, say, something like a quadratic to this curve, and using, instead of splitting it into two segments?
No, you can try to put some curve to this relationship. Split just came up because this is, to many people, seems to be the simplest way to go about it. But it's, of course, not the only and not the best way to go about it. So you will hear about other methods and application of those methods in further talks.
Maybe time for one more question. Although, we've got a longish coffee break, so we can overrun for a wee bit. But, yeah.
Yeah, is it possible we have the data that can show this data point on the graph?
Sorry, I don't understand.
You know, for the Parkinson data, is it possible we have the underlying data that brought out all these points on the graph? so that at least we can look at something like cause and effect.
Or you are asking about connecting actual data to those residuals.
Exactly, yeah, if it's
Yes.
possible.
We don't have it right here, but it's very easy to get access to the actual data because it's a data set in the survival package. So we could kind of, not right here, but say somewhere with a laptop and with R, play a bit with the data and show you how it looks like.
Yeah, so maybe as a
I mean,
follow-up.
if, for example, high blood pressure is one of the data, then we can say somebody that has a Parkinson disease, if the blood pressure is high, then we can say it will definitely demonstrate on the graph. That's what I mean. If we can see the...
In this particular instance, there is no blood pressure in this data, but
No, I'm just using that as an example.
Yeah, but we will show you much more kind of detailed examples which are our own data, and say, yes, we will see lots of other predictors, such as blood pressure in particular, yes.
But I think more as a sort of something to do after the workshop is that it might be useful for everybody to get a pointer to the data set and also some follow-up in terms of the packages, because it may be very useful for people in the audience just to try out some of with that particular data set, just to try out some of the techniques and the packages, because it's quite a good way of just doing a bit of hands-on learning.
Yes, that's a good idea. We will upload a list of packages and a list of data sets so that you would be able to play with them on your own if you want.
Yeah. And obviously, I'm guessing that whereas that data set is publicly available, whereas your data has huge confidentiality
No, we can't
issues.
put raw data.
I'm interested in why the graph is being split at 9, whereas, I mean, looking at that by eye, I'd be saying probably 3 and 12. So could you just talk through why you chose to split it at 9?
As I said, the decision was arbitrary. I kind of think that from about 9, the black line seems to be flat. Isn't it?
So it's the black line rather than the confidence interval that you're...
Yeah, it's the black line, because confidence interval becomes wider because we have less points.
Right, okay, thank you.
Yeah, but the black line is the central dependence on time of the coefficient. And it looks like from 9, it is more or less constant.
Okay, thank you.
Okay, well, I think we've come to a sort of natural pause. So we've got about 25 minutes now for a coffee break. But before we do that, can we thank Elias for his first presentation?